So let's get started with our actual calculus stuff. Oh, this is going to be awesome. So with our calculus, we're going to talk about limits first. Now, our limits is really the basis to our calculus. It's how we do calculus. We're going to find out some kind of tricks to calculus later, but for right now, if you know how to do limits, you're going to be able to do calculus. So it's probably a pretty important idea, yeah? Yeah. So we're going to find that out towards the last part of this class. For right now, I want to lead you through an introduction to calculus and what it's all about. Are you ready to learn that? So review is over with, thankfully. Now we're going to slow down just a little bit. We're going to talk about actual calculus stuff. So no more really hair-raising, kind of, oh my gosh, so much stuff. We're going to go a little bit slower, but it's going to be more in-depth. You ready for it?
Yes. I said yes. Slower pace sounds good.
Slightly slower, not much slower. In calculus, we have two basic goals in Calculus 1, this introductory course of calculus. So here's our two goals. Goal number one. The first goal, and the one that we're going to spend most of our class on, at least the first half of our class on, is this goal. Given any curve, not straight lines are easy, but given a curve, I want to be able to find the slope of a curve at a point. Isn't that an interesting idea? If I say to you, I want you to go ahead and find me the slope at that point. Right now, we really have no idea how to do it. I mean, you can approximate it. You can go, oh, okay, I'll find you slope. Let's see, slope is 1/2. Is that accurate? No idea. Right? Well, we can't really just kind of approximate slope. What we're going to do is find out a really good way using calculus on how to find the slope of a curve at a point. In fact, when I ask you a certain thing in this class, you're going to say, oh, it's the slope of a curve at a point. We're going to talk about that for a long time. That's goal number one. Goal number one is to find the slope of a or to find the tangent to a curve at a point. The tangent is the line that intersects a curve at one and only one spot in an area. So goal number one, find the tangent which involves the slope of the curve at a point. That's goal one. If we can do that, we're on calculus fast pace. That's good. So we want to take a curve, be able to find the slope of that curve at a point. That's going to lead to the tangent and vice versa. Tangent and slope go hand in hand for us. Goal number two, which is the last half of our class, maybe a little less than that. Goal number two it's also a really interesting question. So cool. By the way, this stuff is stuff you can't answer in any other class, right? You can't do that with algebra. There's no way you can do that with algebra. You can't find the slope of a curve. Are you kidding me? Slope of a straight line? Easy. Slope of a curve? Wow, it's weird. Is that not an intriguing idea to you? It should be. If you're in this class, you'd be like, oh, that's kind of cool. How are we going to find the slope of a curve? I don't know. Calculus. The next question is probably even a little bit more interesting. Next question is, let's suppose I have some funky, any curve that you can think of as long as it's defined by a function. Can you, between 2 points, find the area under that curve? Can you do it? The answer is right now, with what you know, can you do that with geometry? Because I could say, okay, great, find the area of something that's curving. Can you do that? No. No, you can't use the area for a rectangle, that's not a rectangle. You can't use the area for a triangle, that's not a triangle. You can't break this up in any way that you have geometric figures, can you? Not even circles, not even with radiuses, because the radius is changing. So the next question is, can you find the area under a curve? Those are the two goals of calculus. Find the slope or the tangent of a curve at a point, and secondly, can you find the area under a curve between 2 points? Interesting stuff, weird stuff, right? It's crazy questions going on here. And amazingly, it's actually not that hard. I think it's easier than pre-calculus. It's easier than that. You don't have to do, maybe not easier, but if you know pre-calculus, this is not such a reach. What we're going to talk about first, we're going to talk about the tangent problem. I'll give you a very intro to this, but I'll talk about it later on. We're going to talk about this for most of our day-to-day. So let's talk about the tangent problem. Are you ready? Do you have any questions on the ideas of the goals of calculus? Do you understand what the goals are? The goals are A, find the tangent or the slope of a curve at a point. That's what we want to do. Goal number 2, after we finish this, we're going to move on to finding the area under a curve between 2 points. Very cool ideas. So let's work on the tangent problem right off the bat. You're lucky you're here today. Okay, this is it. This is like the fundamental idea of calculus. This is so cool. We're going to figure out what a limit is from doing this idea right here too. Here's the tangent problem. The tangent problem says if you give me any arbitrary curve, so I'm just making up, I don't even know what that is. It's just an arbitrary curve, and you give me a point. Let's call that P. Give me a point, call it P. I want to be able to find the slope of that curve at point P. Do you get the idea? We're talking about the tangent problem right now, right? Slope of that curve at that point. Because if we have the slope and we have the point, we can make the equation of a tangent. Do you get me? That's pretty easy. That's just y minus y1 equals mx minus x1. So right now we have the point. What we're worried about is the slope of the curve at that point. Do you follow? Now the problem is this. If we're going to make a tangent line, how many points do you need to make up a line? How many points do we have? That's the problem. Right? How are you supposed to make the equation of a line when you only have 1 point and you don't know the slope yet? Do you see the issue? That's the problem. So here's what we're going to do. We're going to say, okay, well, let's put some point somewhere else on this thing. How about Q up there? If I connect these two things, if I connect those two things, do you remember what it's called when you connect 2 points together? It's not a tangent, it's a, do you know? It's a secant line. If you've had some geometry, a secant connects 2 parts of a, well, usually a circle, but of any function. So we would say that PQ is a secant line. It touches 2 points of this curve. Now here's the question, all right? You agree that we need 2 points for a line, yes? But we also agree that we want the tangent of point P. That's the ultimate goal here. So my question to you is PQ a good approximation for the tangent? Is this a good approximation for this? Okay, it's an approximation, right? They're both positive, okay, sure. What I'm asking you is there a way, think about this for a second, is there a way that I can make this secant approximation better to make it more approximate the tangent? Can I make this a better approximation? How could I do it? Let's assume for a second that P is fixed, but Q is movable. You can move the point Q. I can't move P, but I can move the point Q. Can you move Q to make this secant line a better approximation to our tangent line? Can you think of that? Where would you move Q? Would you move it up? Would you move it down? Let's look what happens. Okay, this is going to be interesting. So we're going to find out what happens as we move Q down this line. So if I move Q here, is that better or worse? Better, because I'm going to have, let's use different colors here. That. This would be like Q sub 1, maybe a different point for Q. If I move it closer, is it going to get better or worse? Better. Okay. If I move it closer, it's going to get even better. If I move it closer, it's going to get even better. If I move it closer, it's going to get even better. when do you stop? Can you move it really, really close? Can you move it so Q and P are the same point? Why not? Because then you only have 1 point. How many points do you need for a line? We need 2. So can we move it close? The answer is, sure, we're doing it right now. Can you move it close? Yes. Can you move it so close that there's no difference between them? Yeah. Can you make it the same point? No. That would fail because we need 2 points. I don't care how close they are, but you need 2 different points, right? If you have 2 different points, you can make the equation of a line. That's great. That'd be fantastic. That's our idea, actually. So we're going to try to move the point Q really, 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 really close to the point P. If we can move it really, 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 really close, that's math speak, by the way. Really, 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 really. That means very, 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 very. If we can move it really, really, really close, then our secant line is going to be really, 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 really close to a tangent line. Do you agree with the idea? So you take this point, you go, let's move it really close. Not really far away, that's a Stuckey approximation. But if we move it really close, move that secant really close, that point really close, that secant is so close to a tangent line that it's not going to make a difference. That's the idea. So let me write some of the stuff out for you. So what we're doing right here, we need 2 points for a line, sure. We understand that. Awesome. So we have the points P and Q. Well, the question we're asking is, what happens as Q gets closer to P? And the answer is, as Q gets closer to P, we just talked about this, we just said this, this is nothing new. As Q gets closer to P, the secant line more closely approximates the tangent line. Now, have you understood that at the first? Okay. So as Q approaches, I'm going to use that word, we're going to use that word limits as well. Approaches, that means gets closer to. As Q approaches P, we get closer to a tangent, or in other words, the secant more closely approximates the tangent. Okay, well that's great. That's great. Oh, one more little note. Why was it that we can't just let Q equal P? What was the reason? Why can't we just say, oh, let's move to P?
Because there wouldn't be a difference.
Okay, there wouldn't be 2 actual points, it'd be the same point twice, and that's a problem. You couldn't make an equation of a line with that. So one little note, we can't just let Q equal P because we need 2 points to make a line. You need 2 points. That would be a problem. Here's the idea of a limit, all right? This is a big, big idea. Here's the big, big idea for limits, okay? The idea is, how close can you get one point to another without them being the same point? So let's say I have 2 points like this. Can you find some space between it? Let's say I move it over to the midpoint. Can you find some space between it? Say move it over to the midpoint. Can you find some space between it? Can you keep doing that for eternity? Between any 2 points, there's a gap. In that gap, you can fill it in with another point. Because points have no breadth. That means that even though we draw them on the board like this, they really don't have any distance between them. So 2 points can get, would you agree, infinitesimally close to each other? That means so close that you can't put anything between them, but there's still some little distance, and then you can get even closer to that, and closer to that, and closer to that. Would you agree to that? So here's the idea behind calculus. It says we can get Q so close to P that there's literally no difference between the secant and the tangent. We can get it so close, we can't let it equal, but we can get it so close that the secant line is the same as the tangent line. That's the idea of a limit. Isn't that kind of an interesting idea? Yes, there are different points, but they're so close it doesn't matter. That's the whole idea. So the big picture for our limits is, if we let Q get really, really, really close to P, the secant will be identical to a tangent. That's the idea. Or approximate it so closely that it doesn't matter. Really, really, really. If we let Q get really, really, really close to P, I'll use a better word, I'll use a more mathy word for that in just a minute. Really, really close to P, the secant will be identical to the tangent. Here's the idea, right? Here's the idea. Now I'm going to replace this really, really, really with a key phrase for you. The idea of really, 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 the idea of moving P or Q really, really, really close to P is called a limit. Moving something really, really close without actually getting there. That's the idea of a limit. Do you kind of understand the idea of a limit? We would say that Q would be in a limiting position. That means we've got it all the way really as close as we can to P, but it never touches P. That's the idea of a limit. It gets really, really close. So the idea of really, really close is a limit. In the most simple terms. This is it. Would you like to see an example of how to actually do this? Would that be interesting to you? How to find the slope of a curve at a point? You want to see that? It's kind of fun. Okay, we're going to work through this. I'm simply doing this to give you an understanding of how limits work and the jump that you can make, okay? We're not going to be doing a whole lot of math like this. I'm just giving you an introduction right now so that you see it's possible with some real math stuff that you've had before without actually teaching you limits in calculus. I'm going to make one limit jump in this problem. I'll show you what it is. But this is stuff that you could actually do. We're just going to use calculus to do it better. You ready for it? Do it more mathematically. Before I go any further, did you guys understand the tangent problem? Nod your head if you're okay with the tangent problem. You understand the idea of a limit? Moving a point really close to, but never actually getting there. Again, why can't we get there? Need 2 points. Yeah, that'd be fun. Okay, cool. Now we're ready. I'm excited. First little step off into calculus land. Do you trust me? You shouldn't. Here's the goal to this problem. I want us to find the equation of the tangent line to this curve at a certain point. Specifically that one. 1, 1. Well, let's go over to 1, 1, and let's put a point there. So P is the point 1, 1. I'm going to walk you through how we're going to do this right now, okay? I'm going to walk you through how we're going to make up a tangent line using this idea. Are you ready for it? Over here on this idea, we had 2 points, right? P's set in stone, you're not going to move P. What other point do we have? Q. We're going to make a point Q. Q. What's the coordinates for point Q? Why don't you tell me? What's coordinates for point Q?
2.
We can't use actual numbers, right? That wouldn't be very good. So I know 2, 4 would be on there, and 3, 9 would be on there, 4, 16, and so on. But I want you to use actual points. In general, what are the points for, or what are the coordinates for any point? X, Y. Very good. Okay, X, Y. So now write down X, Y. And have your eraser handy. Have your eraser handy because I'm not going to have x, y. I want to keep this in terms of one variable. Now, using your knowledge of what the function is, what's the function? Y equals what? Wait, say it again. Y equals what? Y equals... So instead of having x comma y, would it be okay with you if I had x comma x squared?
Yep.
Yes, no? Because y is x squared, right? So that won't matter. So erase that, and I want you to put x squared. Cool. All right. All right. Now we have this secant line going from P to Q. P is a fixed point, 1, 1. Q is a movable point, x comma x squared. Would you agree that any point on this line will have the coordinates x comma x squared? No matter what I plug in, right? So that movable point, that's going to have the same coordinates all the way down. Now we have this secant line. Here's what we want to know. We know that the equation for a line is y minus y1 equals m x minus x1, true? What we're trying to find is the equation for a tangent line. Here's what the equation for a tangent line would be. Pay close attention. It would be y minus y1, that's the same, equals the slope, but a specific slope. It would be the slope of the tangent line, true? Whatever the tangent line slope happens to be. So the slope of the tangent line, and then x minus x1. Now, the cool part about this, I'll recap this in just a bit. The cool part about this is we already have a point. What's my fixed point that I have? I already have 1, 1. So really what this comes down to is, can you find the slope of the tangent? That's why I said finding the slope of a curve at a point is the big deal for calculus. You already have the point. That's the easy part. The slope is the hard part. So we're going to try to find right now the slope of the tangent. Are you ready for it? You sure? We're going to use the idea of slope of a secant. So we're going to take a break right now. We're going to come back to this. In case you're just a little bit lost, here's what we've done so far. This is y squared, I gave it to you. We've fixed one point according to my problem, that's 1, 1. We've made up another point, a movable point, q. Q is that x comma x squared. Where did the x squared come from? That's because it's y. All right, great. We now know that the equation of a line is this, so therefore the equation of a tangent line would be the same exact equation. It's just we'd have the slope of the tangent line. The problem is, it's very hard to find the slope of a tangent line without doing the limiting idea. You can't do it because there's only one point there. So we're going to have to use the idea of a secant and make it into a tangent line by moving Q really close to P. Did you get the idea? Basically doing that with this problem. So let's take a look at the slope of a secant. Our specific secant. Hey, by the way, do you remember the slope in general, the slope formula? Slope is what over what?
Right.
Okay, great. In terms of our coordinates, slope is delta y over delta x. Specifically, in terms of our coordinates, what is our slope? That's what I'm looking for. y2 minus y1, yeah, over x2 minus x1, otherwise you get the negatives of that slope. So y2 minus y1, x2 minus x1. Do you follow? How many people feel okay with this so far? Just slope formula. What we're going to do, we're now going to find the slope of our secant. We've got the secant on the board, right? The secant will be the slope, I'm sorry, the slope of the secant will be the slope from points P to Q. Agreed? Let's plug in these coordinates. We already have them on the board. Plug in these coordinates into that formula. In our case, our y2 is what? Our y2 would be x squared. What's our y1? Not x. Would be 1. What's our x2? What's our x1? Okay. y2 minus y1 over x2 minus x1. Not sure if you're okay with that. So what we'd have for the slope of our secant is y2 minus y1 over x2 minus x1. Are you okay with this so far? Find out where the slope comes from. There's a couple notes I want to make at this point. First, I'm reiterating a lot of stuff here. I know that I am. I'm doing it on purpose because these are the key points of calculus, all right? You need to understand what we're doing. I would hate for you to get through this class, right, and at the end of it, know how to take derivatives and integrals and have no idea what you're doing. You can be successful on just doing derivatives and integrals in this classroom. But if you don't understand what it is you're actually doing with those things, you don't even know what they are right now. But if you don't understand what you're doing, it's irrelevant. You're just doing formulas. It sucks. If you know what it comes from, what you're actually doing, I'm going to make sure you know, by the way, it's a little bit more interesting and you can apply it to more things. Do you get the picture? So right here, what we're doing, step number 1, is if we move Q close to P, this is going to become this. Do you agree? As Q, I'm going to use a new symbol here, approaches P. That means as Q gets really close to P without touching, the slope of the secant line approaches the slope of the tangent line. Would you agree with that statement? That's over here right now. You agreed with it already. Haha, I tricked you. As Q gets close to P, the secant gets close to the tangent. True? That's what this says right now, okay? As Q gets close to P, the secant gets close to the tangent. How close? It depends on how close we get these things. If we get them so close it doesn't matter, then these become so close it doesn't matter. Agreed? It's kind of neat, right? It's a cool idea. Now, the problem is, here's note number 1. Here's note number 2. This is interesting, right? Where are we trying to find the slope? What point? 1, 1. Well, and what's the x-coordinate for 1, 1? To find the slope of anywhere, you plug in that value, right? This gives you the slope of the secant line, true? Plug in 1. Plug in 1. What happens? No, you don't get 0. You get 0 over 0 over 0 is not 0. That's a big problem. 0 over 0 is undefined, right? Isn't that an issue? This is why, folks, this is the reason why you cannot have the point getting, listen, you can't get Q close to P because if you plug in 1, it's undefined. That means that you have the same point. So you can't let x equals 1, that's big time. That means double important. You can't let x equal 1. This is why we can't let Q equal P, because we only have 1 point, right? You can't find the slope. It fails. It's undefined at that point. This is why Q can't equal P. If it does, if you try to find the slope of the secant at that point, move Q all the way down and then plug in the x-coordinate. If it's the same thing, you're going to get something that's undefined because you're trying to find the difference between points that don't exist, a difference that doesn't exist. And that's going to be, you're divided by 0. There's no difference in the x-axis. That would mean you're divided by 0. You get something that's undefined. You get an undefined slope. That's a bad thing. So we can't let Q get all the way to P. True? All right. What can we do? Now this is going to blow your mind. You ready to get your minds blown? Like a mind grenade. You ever seen Yes Man? Watch Yes Man. It's so fun. I had a Ripple. Y'all have Ripple? Let's go on Ripple. Right. If you've not seen it, that just sounded really stupid. You watch Yes Man, it's pretty funny. Now, so, next part. Gonna blow your mind. Can you factor that? In fact, learning what we knew about asymptotes and stuff like that, you know that if you have 0 over 0, it's factorable because of some stuff in mathematics that I haven't bored you with yet. But if you ever have some number that makes 0, it means that that's a factor. If you have some number, the same number that makes 2 polynomials 0, it means they have a common factor. We've got a common factor here. In fact, if you were to factor this, this is going to give you x plus 1, x minus 1, over x minus 1. Agreed? Okay. Do you see anything that simplifies out of that? Aha. Now this is cool. Now this is interesting. Very interesting. What we're going to do is we're going to be able to simplify out this thing. Now I know what you're thinking. Well, wait a second. Can't you not simplify out a domain issue? Isn't that a problem for you? And the answer is Yes and no, it would be a problem normally. However, watch carefully. Are we actually letting x equal 1? Is q actually getting to the point P? No. So is x actually equaling 1? No. We're getting really, really close. I'm talking like 1.00000 forever and then a little bitty 1 at the very end of it. Really close. But it's never actually equaling 1. So keep in mind, when we do this, we're not getting rid of any, we're not really altering the domain whatsoever because we already knew x wasn't equal 1. So we have this little restraint already, x isn't going to equal 1. So then what we know is, okay, the slope of the secant now equals x plus 1. Were there any questions on this? Because I got to erase it. Do you have anything? All right. Is this making sense to you? Do you see where the slope formula came from? Do you see how we can factor and simplify it? And now we get down to here. We don't have any problems. We're not eliminating domain issue because we're actually not letting x get equal to 1. It's just getting really close to it. Here's the jump that we're going to make, okay? Here's the jump. So that was true. That's what we have down. What I'm asking you is, as q gets closer to p, so basically as x gets closer to 1, what happens? As q gets closer to p, that means the x variable is getting closer to 1. As x gets closer to 1, can you tell me what happens to the value of the secant? Let's try some, okay? Think about this for a second. Just do a little bit of math with me. Let's say we started at the point 416, so x would now be 4. Plug in 4 here, how much would you get? Okay, now let's move it down to 3. Plug in 3 here, what would you get? Move it down to 2, how much would you get? Okay, move it down to 1.5, how much would you get? 2.5. Move it down to 1.3, what would you get? Move it down to 1.1, what would you get? Move it down to 1.01, what would you get? 2.01, good. Move it down to 1.00001, what would you get? Move it down to 1.00000 forever, and then a little 1 at the end. What would you get? 2.0 forever and little 1, wouldn't you? Would you say that as this thing gets closer to 1, the slope of our secant gets closer to 2? Would you say that? Because I'm plugging in things really close to 1, I'm going to get out things that are plus 1, really close to 2. Does that make sense to you? Our secants will be really close to 2. Here's what that says. This lets us make the jump. This is a limiting position. It says that we know the limit of the slope of the secant line is 2. What that means for us is that the slope of the tangent line actually is 2. That's the jump. It says the secant line at this point, if x gets super, super close, really, really close, if x gets really, really close to 1, the secant line gets really, really close to 2. Now I can't let x equal 1, but I can make the jump that if I could let x equal 1, the slope would be 2. That's the jump there. Do you guys see the jump? This is the using limits to make the jump between a secant and a tangent. So because the secant's approaching 2, we say, okay, we got this. That's called a limit. We're going to talk more about limits later on. But the jump is going from here to here. Now can you fill out this equation using that information? Sure. We know that it would be y minus y1, which is 1, equals the slope of the tangent. Hey, we know it's 2, x minus 1. Now, of course, we don't generally leave things in point slope. We'll solve them. Do you see where the 1, and the 2 are coming from, folks? Our point is 1, 1. Our slope is now 2. That's the slope of the tangent. If we solve it, we get y minus 1 equals 2x minus 2. Add the 1. Y equals 2x minus 1. That's the slope of a curve at a freaking point. That's awesome! Oh my gosh, isn't that cool? We just found the first tangent line to a curve that you've done. Now granted, it's not a very hard curve, but here's what it is. I'll show it to you. You can actually graph it. Here's minus 1, it crosses there. You go up 2, 1, 2, over 1. Oh, that's the point. And if I graph it, it intersects at only one spot. That's it. That's a tangent line. Isn't that awesome? Your mind should be blown. Is that why you're looking at me stunned? Like,
Yeah.
is that your stunned face? It should be your stunned face. Okay. Now, by a show of hands, after 40 minutes of doing one example, how many people understood what we talked about? Good. Do you have down right now the basic idea for calculus? This is the basic idea. Using limits to find this tangent of a curve at a point. Is it going to get more advanced than this? Yes, of course it is. But that's the basic idea. Now we're going to do things differently when we actually get to the calculus. We need to study limits more first, but we will get there. Now the next thing we got to talk about is the different problem. I'm not going to spend a whole lot of time on it. I'm basically just going to introduce it to you because I know for sure you guys are not going to remember this by the time we actually get to area under a curve, so I'm going to reintroduce it to you again. But for right now, I want you to just get the idea about what's going to happen later on. Okay, so the area problem. Here's the area problem. Area problem says, can you find the area under a curve between 2 points? The answer is yes, you can with calculus. Only how are we supposed to do this thing and let limits work for us? Here's the plan. Firstly, can you find the area the way it is right now? No, it's got a curve to it. You can't find areas with curves in them. So what maybe would be an idea?
You can approximate it by making it like a rectangle.
Oh, I could, yeah, sure. If I did this and said, okay, from here, I just want to make a rectangle. Would that be an approximation? Mm-hmm. Would it be a good approximation? No, not really. However, what if I did, okay, I don't want just one rectangle. Maybe I do this. I say, okay, I want a rectangle from here to here, then a rectangle from here to here, then one from here to here, and then one from here to here. Is that a better approximation? The missing area is smaller, yes? That's the idea behind the area problem. What we're going to be doing is making rectangles. Why rectangles? Well, let me ask you, can you find the area of a rectangle? That's why rectangles. And they're easy to draw. That's what I have. So if we make lots and lots and lots of little, itty, teeny, bitty, weeny little rectangles like that, all the same width, but going the entire length of our curve, and we add up all those rectangles, are we going to have a pretty good approximation of the area? And in fact, if we make those rectangles infinitesimally small, so whereas you couldn't even slip a piece of paper between them and then add them up, is that going to be even better? In fact, if we stuck an infinite number of rectangles between this point and this point, which you can do with limits, we're going to have a perfect area, and that's the idea for the area problem. You stick an infinite number of rectangles in there and add them up. It's going to involve limits because we're letting some number go to infinity. You can't ever reach infinity, but a limit will take care of that for you. That's the idea behind the area problem. Does it make sense? Kind of? The idea of the rectangles? Trust me, we'll get much more involved later. You have no idea how to do this right now. Don't worry about it, okay? We're not even going to do a problem. We'll do that later in chapter 4 or something like that. So, let's define a limit. What a limit says in English is, what does the function do as a variable approaches a given value? That's what it says in English. So limits. What does the function do as the variable approaches a given value? That's the question. Now, do we care what happens to the function at that value? The answer is no. The limit isn't about getting to the actual point. It's about what happens as you're approaching that point, getting really, really close. You see the difference there. In the previous example, we couldn't actually get to 1. Do you remember why? Some of you are zoning. You're zoning out. Can't have 1 point on the line. We'd also make a undefined point, right? If we undefined, that would be bad. But we saw what happens when we get really close. The function got really close to something else. That's the idea of a limit. So we don't care what happens as you get to the value. What happens as you approach the value? For us, this is exactly what we did actually, kind of in our heads. What happens? What happens to x squared as x approaches? Let's do 2. That's x approaches 2. I could have written it in English, but that's just as valid. What happens as x approaches 2? Now, do we care what happens if you plug in 2? No, don't care. What I care about is what's going to happen if I draw this table right here with x and f of x. And I say, I'm trying to get to 2. I don't care what that value is. What I'm trying to see is what the function is doing as I'm getting close to that thing. So what's happening as we approach it from the right? What's happening as we approach it from the left? Give me some, oh yeah, I already ruined it. Give me some numbers to the right of 2. Some numbers to the right. 3. Give me something smaller than 3. Like 2.5. 2.5 is good. I like that. That's what I was about to write. That's why I almost ruined it. Give me something a little bit closer to 2. Closer than that, maybe. 2.1. Yeah, or 2.01. We want really close, right? So 2.1, and then maybe 2.001. That's pretty close. Take your calculators out, by the way. Now let's go the other way. Give me a number that's smaller than 2 that we want to work our way up from this way. Okay, sure. How about we keep it kind of symmetrical? 1.5, I like that one. We'll do 1.9, all right, and 1.999. How about that? Does that work for you? Take those numbers, our function's x squared. Let's look what happens to the function as we plug those things in. If you plug in 2.5, what do you get when you plug 6.25 or something like that? Plug in 2.5. Do you get 6.25?
Yeah.
Okay. So we'd start with 6.25. What we care about is, does this side, look at the board, if we go this way and we go this way, do they meet up at the same point? That's what we're talking about for limits. Now this is a very easy example. We're working with x squared. We know the answer is going to be 4, right? Or at least it should be 4. We're going to see if that actually happens when we evaluate our limits. Plug in 2.1, someone out there. Tell me what you get when you plug in 2.1, would you? 4.41? Okay, that's closer to 4. Tell me what you get when you plug in 2.001. 2.00. Wait, what's it?
4.004001.
How about that? Like that? How about 1.5? Oh, that's 225, isn't it? How about 1.9? Plug in 1.9. What do you get when you do that? X squared. 3. And now do 1.999. 1.999. What do you get? How much?
3.960.
3.960?
Come on.
Yeah? Okay, cool. What's going on here? Let's see. With a limit, we really don't care about what happens at 2. Because a lot of times what you're going to find out is that we deal with limits where you can't get to that number because for some reason it's undefined, like our slope problem we just had, okay? So we're trying to figure out what's happening from the right and from the left and see if those are heading towards the same exact value. Are they? We're going from 6 down to 4, down to 4.04. Where's this heading?
Towards 4.
Where's this heading? It's heading towards 4. What we would say right now, This is how you write it. Couple notes about this. The function must approach the same value from both the left and the right. So this is from the right. This is from the left. The function must approach the same value from the left and the right for the limit to exist. If it does, here's how you write the limit. What you do is you put a little lim undercase, which kills me because I can only write in capitals. So you put the limit, you put the variable you're working with, you put that little arrow, which I already told you is approaching, and you put the value to which x is approaching. X is this one. Where are we trying to get to on our x? We're trying to find out what happens around the point x equals 2. Does that make sense to you? So you'd say the limit as x approaches 2 of your function. What was our function? Say it again. X squared. The limit as x approaches 2 of our function is equal to. What did the function approach? Here's what this says in English, okay? Look at the board. What does the function approach as the value x approaches 2? What's the function approach as x approaches 2? What's it get to? That's the limit. In general, we have this. This will be the last bit. We have a limit of a function is equal to some number. That's what capital L is. That would stand for the limit of this function as x approaches a. It's what the function's tending to do from both sides as x approaches one single value. The only thing that we need to know is the limit really doesn't depend on getting to a. Or x is never going to equal a. X never gets a. We just care about what's happening to the value of the function as x is getting really close to a from both sides. Up here on the board, what's happening to the function as x is getting really, really close to a from both sides. It's getting really, really close to 4. That's the idea of a limit. How many people understand the idea of a limit? Cool. Next time we'll work on how to find some limits. All right, so if you remember from last time, we're talking about limits, and what we're realizing is that a limit basically says or asks the question, what is the function doing, what's the value of the function doing as x approaches a certain number? Now, do we ever care what happens when x gets to that number as far as a limit is concerned? No, not really. Just what's the function doing? Where's it getting close to as we're getting close to that x value? And that's the idea here. So when we're talking about the limit of x minus 1 over x squared minus 1, that's our function, we want to find out what happens as x approaches 1. Now, why can't I figure out what happens when x equals 1? Tell me that.
Makes your denominator 0.
That would be undefined, right?
Yeah.
As a matter of fact, it makes both the numerator and denominator 0, and that would still be undefined. We found out that is that a whole or an asymptote? Do you remember? That's a whole. That's going to be a whole. That ultimately, this function has a whole. So what we want to find out, though, is what's the function doing as we approach that certain value. Now, one way we figured out, the only way we figured out these limits, is to make up a table. And this is kind of the elementary way that you discover limits right when you first learn. Now, towards the end of the day, I'll teach you some better ways on how to do this. For right now, though, I want you to see what happens with the function with the limit. So when you are finding these, and your homework's going to ask you for that, find the limit of this function by making a table of. When you do that, you have your x values on the top, you have your f of x values on the bottom, in this case, x minus 1 over x squared minus 1, and you start with the number you want to find the limit of, the number that you want to find the limit of the function where x is approaching that certain value. Put that in the middle. So for instance, you're going to put 1 right there. And really, I don't want to know what that is, because you can't plug it in anyway. What we want to find out is what's happening from both sides. Is it going to the same value? You follow me on this? So, what you need to do now, put these numbers in order because it is a number line. You don't want to have like, I see a lot of mistakes on this. I see a lot of people do this. Okay, well, I'm going to start at 2, and I'm going to go to 1.5, and then I'm going to go to 1.1, then I'm going to go to 1.0001. Right. Do you see how that's the wrong way to do it? That's going to show you one direction, but it's the wrong direction. You need to have these numbers reversed so that this is just a little bit past 1. We're coming from the right-hand side. So if you want to find out where it's coming from, don't have 2 right here. Have 2 over there somewhere if you're going to do that. All right, so these numbers that we have next to 1, they should actually be the numbers that are close to 1, all right, not the other way around. Are you following that? Nudge your head if you're okay with that. So we don't want to have the smallest numbers over here that are the ones that are closest to 1 over there. We want this just like a number line would look. So here, maybe we do start with 1.5, 1.01, 1.001. Make it really close to 1. Now the other way, I'll probably want to start with 0.5, right? I want to make it symmetrical at least a little bit. So where's 0.5 going to go? Is it going to go by the 1 or over here on the left-hand side? Left-hand side. Now I want the numbers that are really closest to 1, well, the closest to 1. That's going to show me the trend. So 0.5, maybe 0.99, and 0.999. What I'd like you to do right now on your own, take out your calculator, find those numbers. How about this? The people to the, let's see, this is your left. The people to the left side of the camera, do these ones, okay? People to the right side of the camera, do those ones. Can you do that for me? So plug them into the function, tell me what you're getting out.
I know there's a way to do this on it. Do you know how?
Have you started to find those numbers? Does anybody have this one yet? 6 point.
6 continuing.
Does everybody got that one? Same one? 6.6666 for everyone? Okay. So 6.67. How about the 0.99? Did anyone find that one? 0.99.
5.0525.
Can I get a double check on that? 5 point?
Yep, 0.5.
How much?
0.503.
0.50. How about for this one? That's the right one? Let's double check that one. 0.99 minus 1, that should be pretty small, negative something. One more double check. What'd you say it was?
We're at 0.5, and then for the first one, 0.6. Yeah, 0.6.
0.66. Is your calculator scientific notation by chance?
No.
Why don't you guys figure out your stuff, all right? I'll come back to y'all. This side. Try this side. Can you give me 1.5?
0.4.
How much?
0.4.
0.4? Can you give me 1.01?
0.497.
How much?
0.497.
0.497? 0.497? Take it. Okay, can you give me 1.001, please? 1.001.
0.499.
0.499? Okay. Interesting. I'm guessing the 6 was probably not all that accurate. Let's try that again.
Oh, no, it was on scientific vacation.
Ah. So 0.6. Okay. Give me 0.99. Point what? 0.503? Give me 0.999. 0.5002? Now, do you see the trend to which this function is getting close to? Can you see it? What number is it getting close to from the right? What number is it getting close to from the left? That's why you put it in this order so you can see where it's approaching from the left and from the right. If it's the same number, if this is getting to 0.5 and that's getting to 0.5, you'd say, okay, that limit exists and that limit is 0.5. Are you following me on this? So the limit right here would be 0.5. And that's how you use a table to figure that out. Now, of course, this was a pretty mind-numbing task, right? Who wants to plug in 1.001 and do all this for a whole bunch of numbers? Do you want to do that? No, I don't want to do that either because it's boring, right? We're going to find some better ways to do these limits in the next section. For right now, though, I need you to get to understand what a limit is. A limit asks, what's the function, the value of the function do as you get closer, as your x value gets closer to that? What's the function's value do? What's the function's value do as your x value gets closer to that? From both the left and the right. If it's to the same number, the limit exists, and it's that number. Raise your hand if you're okay with this so far. Now, are there ever cases when the limit doesn't exist for a number? I want you to look at this, all right? We're going to talk about something called one-sided limits. And the question is, what's the limit as x approaches 2 of f of x? Now, what we've had on the board already is what's called a right-sided limit and a left-sided limit. You have this kind of intuitive idea, right? In order for a limit to exist, it's got to go there from both sides. Does that make sense to you? It's got to get there from both sides for the limit to exist. So from the left and from the right, it has to be the same number. I want you to look at this thing. Which way would be from the right? Over here or over here? Option 1 or option 2? From the right would be this way, true? We can actually have right and left-sided limits. So here's how you write that. A right-sided limit in our case would be a limit of our function as x approaches whatever value you're talking about. In this case, we're talking about the value 2. Do you guys see where the 2 is coming from in this case? We want to find out when x approaches 2. And how you say from the right-hand side is you put a little superscript plus. That means from the right. So in general, you'd have this. You'd have a limit of f of x as x approaches some number that I give you from the right. That says a right-sided, one-sided, right-sided limit. Nod your head if you're okay with that. So plus means from the right. You all right with the plus meaning from the right? What do you think a left-sided limit is going to have? Ooh, you guys are geniuses. Exactly. Yeah, left-sided limit would be a limit of f of x, sure, as x approaches a certain number. In our case, our certain number is 2. And that little minus or negative is from the left. In general, we'd have the same situation, only from the left. So let me ask you a question. Can you find the limits, both right-sided and left-sided, of this function? Let's try that together. Here's what the question, I'll go nice and slow so you can understand it. Here's what the question asks. what is the value of the function as x approaches 2 from the right for a right side and from the left side. Okay, so follow the function along. I need you to tell me what the height of my finger is. What's the height of my finger when I get really close to this value along this line? So this is from, am I going from the right or the left in this case? From the right. From the right. Okay, it's always from the, it's not to the, it's from the right. So from the right, the height of my finger is, okay, I'm a little above one, a little above one. What's the height of my finger going towards as I slow down? I'm slowing down. What's the height of my finger trying to get to?
1.
It's trying to get to 1. Do you see that? It's not that my finger's getting close. It's not the limit's going to be 2. It's saying what happens to the value of the function. The value is your y-axis. What's happening to the value of the function or the height of my finger as my finger is approaching in this direction, the number 2. Does that make sense to you? So here, the height of my finger is trying to get to 1 as I'm approaching 2 from the left. That's what I said. From the right. I'll edit that out. You won't even know. Beep. Just kidding. I'm not going to edit that. It's going to be on there forever. Yeah, so from the right. So from the right, it's going to be approaching 1. Yeah, thanks for that. You okay with that being 1? It's either yes or no. If you're not, that's okay, but I need to know. I need to have a question from you if you're not. Are you guys okay with the height of that being 1 as this function's approaching an x value of 2? So basically you're asking what's the y value when you reach your x value?
Okay. We couldn't
All right.
see you.
What's your y value when you reach your x value? So now we're going to do it from the left-hand side. What's the height of my finger, aka the y value, as I approach the x value of 2? So what am I doing? Where am I getting close to as I'm getting to 2 from the left-hand side? What am I getting close to?
-1.
-1. Yeah, absolutely. Now here's a little note. Here's a little note for you. In order for a limit to exist at a point, the left side limit must equal the right side limit. If it doesn't, then the limit doesn't exist. Does that make sense to you? It's got to go to the same place, otherwise the limit doesn't exist. You can be one-sided, sure, here, here. But if it's not the same spot, then you'd say overall the limit means from both sides. The general limit means from both sides. So if it's not going to the same thing, that limit doesn't exist. So let me write that out for you and I'll explain it. For a limit to exist at a point, we'll call it A. For a limit to exist at A, in other words, for this to happen, for you to be able to say the limit as x approaches A is some number, for that to happen, you must have this. The limit of f of x as x approaches A from the left must be equal to the limit of f of x as x approaches A from the right. It's got to happen. So let's see if that happens. What this says in plain English is this. Ready for the plain English part? Here's plain English. The function from the left and the function from the right have to have the same value. Basically, they've got to meet up somewhere. You with me on that? So let's check this out. Does the function from the right and the function from the left meet up? What do you think? Do those lines meet up? They do? They meet up? They come to the same point? Same value, same height? Well, let's see. This limit was 1, this limit was -1. Is 1 the same as -1?
No.
So, does both the one-sided limits have the same value? No, you'd say this limit does not exist. So we'd say the limit as x approaches 2 of f of x does not exist. This says why? This says the limits from the left and the limit from the right must be the identical number. Do you remember this example? Look up here on the board. Remember this example? Hey, you said the limit existed because that's 0.5 and that's 0.5, basically. It's coming to 0.5. You with me on that? What if this was 0.5 and that was 7? Would that be the same number? Now, this one's 1, this one's -1. Is that the same number? That limit doesn't exist. Okay? It says that you have to have the same function value on both the left and the right. Both. Would you like another example of this?
Sure, yeah.
Why not? May as well.
We have time.
Let's practice. Okay, let's get some good practice. If you're not getting it, I need some questions out of you because you really do have to understand this before we go any further. So, here's the idea. In order to find the limit at a certain value, in this case, we're going to talk about 2 again. Do you see why that would be the interesting case here? I want to break it down to you, all right? If I asked for the limit of 3, it's not very interesting because look at, here's the value of 3. Does the limit exist at that point? Answer's clearly yes. At 3, yeah. Look at the function's there, the function's there, the function's there. It's all the same. Do you get me on that? That's not an interesting example. That's boring. That just says the function is completely there, therefore the limit must exist. From the right and from the left, you're coming to the same exact point. Do you get me on that? That's not interesting. If I ask you about 2, though, that's more interesting. You need to be able to find the limit from the right and the limit from the left as we're approaching an x value of 2. In math, that means this. Can you do this? Can you do this? And can you determine this? Let's see if you can. Let's see if you can. I'm going to give you about 5 seconds between each problem to see if you can get it, okay? So right now, I want you to determine on your own, can you tell me, don't say it out loud, okay, let everyone do this. Can you determine on your own the limit of g of x as x approaches 2 from the right? Do it on your own, don't say it out loud. Give you about 5 seconds. The question in English asks this. What is the y value when x gets really close to 2 from the right? That's what the question asks. What is the function value or the y value when x gets really close to 2 from the right? Well, that was like 4 people answering. Do you all not know it, or do you know it?
No.
If you don't know it, then that's fine, but you need to tell me. If you know it, then say it. Can you find out that the function value, the y value, is about 3, or is getting close to 3 when x is getting close to 2? Can you see that? Because you're following this along, right? You're going, okay, what's happening as I'm getting close to the value 2 along x? The y is getting close to 3. So this is how much? It's 3. Okay, now I want you to do this on your own. Don't say it loud again. Find me the limit of g of x as x approaches 2 from the left. Write it down in your paper. Don't say it loud. From the left. Basically in English that says, what's the y value when the x value is getting close to 2 from the left? Starting from the left. What is it? 1. Did you all get 1? How many were able to find 1? Good, okay. Here's how you tell if the limit exists or not. Here's how you tell. You look at these ones. Are they the same? You sure? Yeah, one's 3, one's 1. I mean, how much more sure can you be? If those aren't the same, does that exist? If those are the same, does that exist? Yeah. I want you to know something really cool, too, about limits. Does it matter at all that that point was right in the middle of nothing? We don't care about that point. We don't care at 2. We care what's happening to the function as we're getting close to that. You see the difference? I don't care about that. It could, may as well not even be there. It doesn't matter. We don't care about that point. We care about the function value, the y value, as we approach the x value. So if this does not equal that, does that exist?
No.
So you put Danny? You can really see it though, can't you? If the lines don't match up, it's not there. It's not going to happen. The limit doesn't exist. Let's do one more and we'll call it good on this stuff. Here we go. Oops. Okay, last picture for us. I want you to try to do that one completely on your own, okay? This is h of x. I want you to find the limit of h of x as x approaches 5 from the right. I want you to find the limit of h of x as x approaches 5 from the left, and then I want you to determine whether or not that limit exists at x equals 5. Do you follow the questions? Okay, go ahead and do that. See what you get. Let's see if we did it right. Okay. So the limit of our function as we're going from the right, as we're going from the left, and then we're going to compare those numbers. So from the right means from the positive, or from the more positive, I should say, because sometimes they're both positive. From the left means from the less positive or negative, whatever your case may be. So from the right, from the left. From the right, what is the y value as your x value approaches 5? What are you getting towards?
3.
Okay, well, what about that one? Does the function actually approach that? Approach it. See, that's the difference. We don't care what it is at that number. We care what it's approaching as we're getting close to that number. You see the difference, right? Okay, so you all got how much?
3.
Perfect. Let's do it from the left. From the left, what's the y value getting towards as your x value is getting towards 5?
3.
Good. Is the right side limit the same as the left side limit?
Yes.
Does the limit exist?
Yes.
Absolutely. Yeah. Why? Don't care what happens at that point. Just because this point doesn't fill in that hole, it doesn't matter. As long as the function's value is going to the same exact spot from both sides, do we care what happens when we get there? No. We don't care about that. We care about this. That limit is 3. How many people have a better idea about the idea of a limit right now? So given a graph, you can do this? Okay, cool. Hey, let's talk about that for a second. What's the one number you can't plug into that?
0.
What would happen if we discovered what the function does as we approach 0? Isn't that an interesting question? It's kind of cool, kind of interesting. What happens to the function as we get close and close to that? Let's talk about that for a second. Now, in order to talk about that, we need limits. What's the function do as we approach that? So just like we did over here, we're going to talk about a right-sided and a left-sided limit, but we're going to do it with a table. Now, what number are we approaching? I'm sorry, what was it?
0.
Where's the 0 go on our table? To the left, to the right, or in the middle? Because that's the number we're trying to get to. Are we ever going to be able to get to the 0? No, we can't plug it in because then it's undefined. That would be a problem. So Now let's pick some numbers that are getting close to 0 from the right. Let's start at like, oh, I don't know, 0.5, and we'll work our way down. So 0.5, is 0.5 supposed to go here or here? The right or the left?
Right.
So 0.5, all right. 0.01 and 0.001. Would you agree those are numbers that are pretty close to 0? Right. What are the numbers to the left of 0? What do you want to use?
Same ones but negative.
Okay, good. They have to be negative, though, because they're to the left of 0. So negative 0.5, that'll work. And negative 0.01 and negative 0.001. So let's use those numbers. Again, left side people, do the left side. Right side people, do the right side. These ones should be a little bit easier to plug in, yeah? A little bit. By the way, this is going a little bit out of the scope of this section at this point. We're talking about something a little ahead of time. 'Cause it's interesting to me, so we're covering this right now. It will come back at us later on, right? But I'd like to make sure you see it in limits at least once or twice before we get to that section. So if you take 1 and you divide by 0.5, I'm hoping that you got 2. Did you get 2? And over here you probably got, well, I'm going to be a genius about that, negative 2. Did you get negative 2? Genius. No. Oh, geez, I hope so.
I divided by the
Okay, good. Whew. I scared myself for a second. So 2 and negative 2, very good. Now, how about 0.01? If you divide 1 by 0.01, you should get, let's see, move the decimal place, you should get 100.
100.
And I'm going to hope this is negative 100. Yes?
Yes.
If you divide by 0.001, that's, let's see, 1, 2, 3 decimal places. You're just dividing 1 by decimal places there, ending in 1. That should be... Let's do a little critical thinking here, all right? First question is this number getting bigger or smaller as we're approaching 0 from the right? Is it ever going to stop getting bigger? 1 divided by 0.00001 is going to be really, 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 really big, right? And it's going to be positive. How about this way? Is it getting bigger or smaller? Way smaller, and it's never going to stop getting smaller. It's not going to a certain number. Now, the second question is, does the limit exist? Are they going to the same exact number? No, in fact, as we're going from the right, where would you say this is going? Because if you draw the picture, it's going like that. It's going where? Infinity. If you divide by smaller and smaller numbers that are approaching 0, keep dividing by 0.00000 forever and then a little 1, you're going to get really, really huge numbers, right? And you can keep getting smaller and smaller still. So what we would say is the limit as x approaches 0 from the right of our function, which is 1 over x, is positive infinity. And you technically don't have to put the plus, because infinity without that plus still means positive infinity, but I want to show the difference. Limit as you approach, as x approaches 0 from the left is, what would you say that would be? Is negative infinity the same thing as positive infinity? So limit clearly doesn't exist. In fact, you can see this from the graph. If you graph 1 over x, your calculator or whatever you graph it on is going to look like this. That's it. You can see as we get towards 0, it's skyrocketing. As we get towards 0, it's really going into an abyss, right? So it's not going to be the same thing. But this leads us to a couple ideas. Whenever we have a limit, I'll write this out for you. If you have a limit as x approaches a from either the right or the left of some function, and you figure out that it's positive or negative infinity. I'll say it again. If you are approaching a number, right, from either the right or from the left, and it's going to infinity, either positive or negative, what that does for you is it gives you an, what's this thing called? Gives you an asymptote. Gives you an asymptote. Because you say, okay, if we're going towards infinity, as we're reaching, as if my y value is going to infinity, as my x value reaches a number, that means I have to be shooting up. If my y value is going to negative infinity, as I reach a certain number, that means I have to be shooting down. So one of those cases, it's going to be some sort of asymptote. You're never going to actually get to that point. You can't. You can't. So there are really 4 cases. I'll draw them over there so that we see them. 4 cases of asymptotes and their relationships to their limits. So the one case is, what happens if we approach A from the right and we're going to positive infinity? Another case would be, what happens if we approach A from the right and we go to negative infinity? Another case would be, well, what would happen if we did the both rights, right, from the right. If we went to A from the left and went to positive infinity. Or what would happen if we went to A from the left and it gave us negative infinity? Would you agree those are all 4 permutations, all 4 cases of this? In either case, we just talked about this, if your function is going to positive or negative infinity, when x is going to A from the left or the right, you're going to have an asymptote. So every one of these is going to be an asymptote. Oh, that's the worst asymptote I've ever drawn. Too experienced. That's the second worst. Oh, that's not bad. Back on track. Let's kind of diagnose what these things would do. I want you to really think of what these limits should do to our function here, okay? Now, if I say x is approaching A from the right, should I start here or start this way? Am I going this way, option 1, or this way, option 2? Option 1. So if the function's approaching A from the right and it goes to positive infinity, should I be going up or should I be going down? So this would be this type of graph. It can do whatever it wants over here. No problem, but when it gets to here, it shoots up. This isn't going to be told by our limit as we approach A, all right? It has nothing to do with it. It's what happens as we get close to A. It's going to be going towards positive infinity. Let's talk about this one. Now, I know we were just coming from the right-hand side. This one's going to be going, well, not up, not positive infinity, it's going to be going down, negative infinity. Do whatever you want over here, but it's going to drop. It's going to be asymptotic to that line. How about this one? Can you picture what that one does in your head already? Draw a graph if you want to right now. You should be able to draw something with that. Are we going option 1 from the right or option 2 from the left? From the left, and should we be going up or down? Which one?
Up.
It's going to positive infinity, up or down?
Up.
Lastly, the only case we have left is from the left going down to negative infinity. It looks something like that. Would you raise your hand if you feel okay with what we've talked about so far today? All right. That takes care of kind of our introduction to limits. We talked a little bit about that. Now, for the rest of our day, I'm going to teach you how to compute limits. Because if you hadn't noticed, this isn't all that fun. I'm gonna show you some better ways on how to do that. Would you like to learn that? Cool. Any questions before we go on?
Yep, just a quick one. The two limits for both approaching infinities, they go towards the same point, or would it exist?
The limit would exist. Yes, it would. So if we have a one-side limit this way and a one-side limit that way, and they both go to positive infinity, yeah, sure. We'd say the limit is positive infinity because it goes from both sides. Or if the limit is going both negative infinity, that would exist. So let's see. This way, yes. This way, yes. This way, no. This way, no. It takes practice to do that, by the way. I showed you that already.
Just one question about this one.
Yeah.
It's approaching from the right, should it be approaching from the left?
This one?
No, the one above it.
This one? This is approaching from the right, going to negative infinity.
Oh, I see the plus now. Oh, never mind. Okay.
Yeah, you know what? Let me write that out too. If this and this do you see the thing here? If we go from the right and from the left, and they both go to positive infinity, then this was your question. Yes. Sure. If this works all the time. If the left side limit and the right side limit go to the same thing, the limit exists. You could substitute in, if this is going to negative infinity and negative infinity, that would be negative infinity. So you can draw that corollary as well. Good question. Any other, thank you for that one. Any other questions before we continue? All right, let's compute some limits. You got that?